Okay, this video covers section 1.1.1 of Griffiths E&M, finishes the vector identities, and we're going to talk about the cross product. So we talked about the dot product in the last video, talked about the cross product here. We define the cross product between two vectors. We can say vector A and vector B. Cross product is denoted by this X. This is the magnitude of that vector A times the magnitude of that vector B times now the sine of the angle between those vectors. And it is no longer a scalar. The cross product between two vectors is itself a vector. This n here is n hat, which is a unit vector which is perpendicular to the AB plane. All right. And we determine which direction n hat points by using the right hand rule. So if I have a vector A and some vector B that are both in the plane of this page or of your screen or however you're viewing this, they're separated by some angle theta, and I do the right hand rule, I see that n hat is going to be pointed into the page, right? A cross B, my thumb points into the page. So the cross product no longer yields a scalar, but it is now a vector. The vector rules are different. It is distributive. You can distribute this cross product, but it is not commutative. You can't reverse the order, right? A cross B is not equal to minus B. Oh, sorry, not equal to B cross A. Right. I fudged a little bit because A cross B is equal to minus B cross A. Right. And that negative sign comes from that right hand rule where you're reversing the order of which vector is first in your right hand rule. All right, you can conceptualize what this right hand rule does. If I have two vectors, we'll call it A and B again. We'll stick with our conventional notation A and B like this. At some angle between them, we already discovered that the vector, the resulting cross product is pointed into the page, but this magnitude, right, we found the direction through the right hand rule, but the magnitude of this is really this polygon that is defined by shapes or by vectors A and B. Okay, another important feature here, just like we did the dot product with a vector with itself to define the law of cosines, we can do the dot product of, or the cross product of a vector with itself. This becomes I'll continue with my notation where I don't use the magnitude bars and no vectors. So this is just A squared times sine of the angle between A and A, and the direction that we have to specify with the cross product. And we know that A and A are pointed in the exact same direction because they are the same. So that means that the angle between A and A is 0, and the sign of 0 is 0. So therefore, the cross product of two vectors with two vectors that are the same is also 0.